This is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering. Today we are going to discuss about B trees. Multi-way trees are the basic trees which have nodes in which the basic part of a node is divided into different categories. For example, in single linked list or double linked list or circular double linked list, whatever linked list which we have learned till date, we know that only one data part will be there. In case of single linked list, we have a single data part and an address. Whereas in double linked list, we have a data part and two address parts. One of the address parts will be talking about the address of the previous node. The other one is going to talk about the address of the next node. If we store data in this manner, ultimately double linked list, which have a very higher importance, which overcomes all the drawbacks of single linked list, we come up to a conclusion that it requires a very, very large space, right? So as every node must store the address of the previous and the next node. To overcome that, even if the case where data is large, the height of your AVL tree or balanced search tree, whatever tree you consider, it raises a lot, as each and every node can store only one database. To overcome that, M-way search trees have come into the picture. So multi-way, M-way meaning multi-way search trees of order M will have at max of M children. Means a multi-way tree will have nodes something in this order. For example, if these are the address data parts D1, D2, D3 and D4, it can have maximum 1, 2, 3, 4 and 5 children. 4 data parts, 5 children. Okay, so and the order of the tree depends upon the number of children it can have. The node which we have just seen is of order 5. So let's see a few properties of the same. So it can have maximum, it can hold m minus 1 keys and it can have m number of children, right? So the keys of the nodes will be in ascending order. Please keep this in mind. We cannot have random data. Okay, there is a very important property which you need to keep in mind. Means, I'll show you with the picture. For example, there is a node over here which have 8 children. Here C1, C2, C3, C4, C5, C6, C7, C8 represents the address of the children. Address of the children of this particular node. As it has 8 children, it is a tree of order 8. It is an M-way tree of order 8, right? So here the nodes have a capacity to hold 7 keys and 8 children. Then the keys are K1, K2, K3, K4, K5, K6 and K7. Keys are nothing but data points. Then what will be the nature of this data? The nature of this data is K1 must be less than K2, K2 must be less than K3 and so on. K6 must be less than K7. Means the keys are arranged in ascending order, right? So the children, the nature of the children nodes will be in such a way that all the children between, say, C2, the child at C2 child will have values between K1 and K2, as it is a child of, say, 2 parents K1 and K2, between 2 keys it is. So the nature of children at C2 will have values between K1 and K2 keys. And for example, let's take a random example. The child at C5 will have values between K4 and K5. Intermediate values I'm talking about. And within each node, all the keys are arranged in ascending order. And each key, based upon the number of children, M-way tree will be given a name. So if it is of order 5, means 5 children it will have. If it have 5 children, it will have 4 keys in hand, right? So now you can understand the advantage of multi-way search trees, because here we can store multiple data values at a single node with a property hidden inside. so that the height of the tree gets reduced when we store huge amount of data. So MV trees are also known as B trees if the order is of 2. If it is an order of 2, it is known as binary search tree. Okay, then B trees. B trees are self-balanced search trees, an extension of multi-way search trees. So it have a few properties which need to be followed. So the basic property is all the leaf nodes must be at the same level. All the leaf nodes must be at the same level. And all nodes except the root must have at least m by 2 minus 1 keys. The maximum of m minus 1 keys. So it is related to property 1. If property 1 is saying that all leaf nodes must be at the same level, you should not have any node with empty data in it, filled in. Data must be there. That is, the keys must be there. Property 3. All non-leaf nodes except the root node must have at least m by 2 data. Means it must have half of the children. You can raise a new node if and only if you have it's half of the children are filled. Not completely. It's not mandate that all the children must be completely filled. At least they must have some data which abides to property 2. Right? So, and there is an exception for the root node. Property 4. If the root node is not a leaf node, then it must have half of the children. It is a hybrid point which comes from property 3. There is an exception in property 3 which says that except root nodes. But what if only a single node is present in the tree? Then it must have at least half of the children must be there. At least m by 2 children must be there. It must be binary in nature. Okay. Property 5. A non-leaf node with n minus 1 keys must have n number of children. That is the basic rule which we have for multi-way search trees. The last property, 6th property. All the key values in a node must be in ascending order. Even this is the basic property of a multi-way search tree. So B tree is also known as a height balanced M-way search tree. It is a height balanced M-way search tree because look at property 1, all the leaf nodes are at the same level. So unless all the nodes at n minus 1th level are filled, n minus nth level will not start, and unless nth level completely fills, n plus 1th level will not start. Right? So this property balances the height of the B tree. Right? Let's look at the applications of B trees. So it reduces the reads made on the disk because once we search in a node, in the root node, so we can see whether the search element is within the root node or not, or else we can come to a conclusion between what keys are that child is existing in which we can find the search element which we are searching for. Right? So thereby we are reducing the search area drastically. I can say even more than half of this search area we are reducing by each and every iteration. Right? So B trees can easily be optimized. Adjust its size according to the disk size. Based upon the disk size, we can easily increase the number of children or raise the order of your tree. So the height will be reduced drastically. It is specially designed technique for holding bulk data. As I was telling from the first point, so it is used to handle huge data. So basically data which holds databases of terabytes like weather monitoring system kind of things, we use B trees. So for reading and writing large blocks of data also, we use B trees. So there is a small example of a B tree of order 4. Have a look at this one. So can you guess how many children this can have, look at each and every node in this tree. You can easily find out what is the order. So look at the root node. It can have 1, 2, 3 and 4 children. So the order of this tree is 4. So let's analyze the same. So as the root node is having 30 and 70 and a null, right? So you can see that 50% of its data is filled, right? And the elements left to 30, all the children node which are left to 30 are having the values less than 30. Have a look over it. So 8, 25, 1, 3, 7, 15, 21, 23, 26 and 28 are the data values which are present left to 30. All are less than 30. Coming to the children between 30 and 70, and the sub tree which specifies this is this part. So look at the keys present in this subtree. All the values are between 30 and 70. Between 30 and 70. From 40, the least value is 35 and the highest value is 67. Right? So coming to the last, rightmost subtree, which is the right part of our node 70. Right? So this will have all the values greater than 70. All the values greater than 70, starting from 71 to 97. If at all we have a value, some value as the third key in the root, then we can say that the values in the right of 70 are between this 70 and the value x, right? So, but right now in this example, we have two values or two keys in our root node. So this property is a recursive property. Take any subtree and its corresponding root, the same property prevails. Okay, let's analyze this point also. Have a look at this one, this subtree. Okay, forget about the remaining tree. Keenly look at this subtree. Okay, so here the root node of this subtree is having values 40 and 50. So all the values left to 40 are lesser than 40, which are 35 and 38. And the right subtree of 40, or even you can say left subtree of 50, are having values between 40 and 50, which is 42 and 49. Coming to the right subtree of 50, will have all the values greater than 50, which is 56 and 67. I hope you got my point, right? So this is a recursive process with which we represent B trees, and B trees have the property. You can see that each and every root and subroot, 50% of its data is filled, right? And all the leaf nodes are at the same level, are at the same level. So the basic operations that we can perform on a B tree are search operation, insertion and deletion. And the complexity of all these three operations is bigger of log n, which is very, very less when compared to the remaining trees. Like you take a balanced binary search tree or binary search tree or binary tree. As I hope you know the hierarchy. So first of all, trees comes into the picture, which is generic in nature, which says that a root and any number of children. There are no rules or laws placed on it, forced on it. So if you put a law saying that it can have a maximum of 2 children, binary trees comes into the picture, right? If you put a constraint saying that the left child of any node must have a value which is less than or equal to the parent, whereas a right child will have a value greater than its parent, binary search trees comes into the picture. So if you put a constraint on BST saying that the balance factor of every node must be either -1, 0 or 1, AVL trees comes into the picture, right? So from that, if on BSTs, if you put another constraint or a different constraint saying that they can have a max of m children, then it will have m-1 data in each and every node, multiple data in each and every node, then your B trees come into the picture. B trees come into the picture. So this is a small hierarchy which I have defined. Okay, so in this manner, if you remember from which tree the new tree is coming into the picture, it will be quite easy for you guys to remember the same. So in this lecture, we have seen an introduction of multi-basic trees. From that, what a B tree is, how it looks like in memory, how it is stored, and what are the properties of B trees, and what are the operations that can be performed on B trees. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.